We've so far talked about the IBM 9020, which is this big beast up here, and that really had two functions. We've talked about flight data processing, which is the information about what the aircraft intends to do, but the other major facet of this is radar data processing. So you can look at it from the point of view that the flight plan tells us what the aircraft intended to do, the radar tells us what it's actually doing. And they're not necessarily the same thing. There's all sorts of reasons why the flight doesn't actually follow the original flight plan. It can be due to weather, it can be due to congestion, there's all sorts of reasons. This was the first time we were able to bring the two together, flight and radar data processing. But that was all this did, it just did the processing. Somehow we have to display all of that lot. So we now toddle over here. And this is an early example of a radar data processing system. It's called the Processed Radar Display System. And essentially what happened was that radar information, which is pure, this is a radar plot of this particular aircraft with no other real information associated with it, would then be routed to this equipment, which would then be responsible for determining which controller needed to see it. So effectively doing the routing. But then also, down at the bottom here, one of the world's earliest graphics cards, a PDP-1134, which was just simply there in order to take the radar data and actually work out how to paint that onto the radar screen. Vector graphics drawn rather than raster drawn, and a very early example of a graphics card. And that in turn, down a jolly great long cable, would feed to this kind of a display here. This is actually a slightly later display, but it's the same sort of general type of display. All that's in here is really the technology that's required to take the graphics generated positional data and actually paint it onto the screen. These screens were outrageously expensive. I think they were in the tens of thousands of pounds back in the 1970s, and they were also rather easy to break as well. So we were always very, very careful with these. These are all different radars that can feed in. So you've actually got a switch up here that selects the different radars. And because this could be run in what's called bypass mode, so the control, this is how we used to do it in the old days, the controller would select whichever radar gave him the best image for the area that he was trying to work on. And those are the various en route radars. So you'd have at least two of these screens, sometimes more of them, for each sector. So this is a sector display.
How big is a sector then?
A sector varies in size depending upon what's going on. There's some sectors, like for example the London TMA, Terminal Maneuvering Area, which is really quite small because there's an awful lot of stuff going on. As you get further and further afield, so the sectors get larger and larger. The other thing that can happen is the sectors can change shape between different times of day and so on. So, for example, at night there's much less air traffic and therefore controlling it is much easier. So you can make the sectors bigger, and then as the traffic starts building up in the early morning, as the flights start coming in across from the States, you make the sectors back smaller again. And that's something else which we were able to do as a result of introducing computers into it. This idea of dynamic allocation of sector size, which before then had been really quite difficult. You might have heard of occasions when there's been a few hiccups with the air traffic control centres, and usually it's to do with changing the size of these sectors. But again, the code's been in there for a long time now. I think we've got pretty well all the bugs out of it. The controller would use this rollerball to, for example, highlight a particular aircraft and draw a vector to indicate how far away he would be in 5 minutes' time or something like that. This predates the mouse really, but in fact in some respects is probably a better system. They are still using rollerball technology for radar display systems even to this day because it's in one place, it never moves. I was up at Prestwick Control Centre just about a year ago and watched them using this to work out, so they've got a radar paint sort of showing that the aircraft is such and such, and we know what speed he's going at, so we can then draw a vector which says that's where he's going to be in 5 minutes' time, which allows them to see whether he's got any issues with collision avoidance or anything like that. And also to just get the timing sorted out, the controller is trying to vector this aircraft onto the instrument landing system, so it's a useful idea if you can sort of say, oh, we'll be at such and such place in 5 minutes' time or 2 minutes' time or whatever. So this is a very early example of the radar display using the data from the IBM 9020. That sounds ever so easy. There was actually lots and lots of steps along the way, and in fact it took many years before the radar data was really being processed by the IBM 9020 and displayed in native form on this type of display. There was also bypass systems because, well, like all of these things, we don't want it failing. So there's always standby systems and standbys to the standby systems and so on, and a lot of that had to be implemented for the radar side of things as well.
What's the sort of refresh on something like that? How often would it be refreshed?
Well, it's effectively being refreshed all the time because it's a vector graphics drawn system, but the radars typically rotate one rotation every 4 seconds. So you're only going to get an update in terms of the radar data about every 4 seconds. And what you actually see is like a little, you see a blob where the aircraft is, and coming off that, there's a line and then a box, and in that box you've got information about the aircraft, its altitude, the aircraft call sign, its type, where it's going from, where it's going to, whether it's ascending or descending. If you've looked at Flight Radar 24, they do a very similar thing. That's using a thing called ADS-B, which is a broadcast positional information system from commercial aircraft, and effectively plotting that using servers, and then you can pick that up on the internet. And what they've done is they more or less followed the same kind of radar display appearance as you would have at a control centre.
Going back to our early graphics card over here, how many of those would there be in the air traffic control centre?
I think it was something of the order of 100, so it was quite a big investment and a lot of real estate as well.
Well, how much were those sorts of things costing then?
I don't know, to be honest. I think they were probably in the quite a few £1,000s each type of category. So, you know, there'd have been large chunks of £1 million worth of equipment there. But back in those days, hardware was very expensive.
Safety first as well.
Yes, the whole idea was that everything was resilient. And of course, this wasn't the only place we were using computers. The computers were coming into air traffic control in just about every sort of capacity. This is the kind of radar display that we have today, and essentially all of the hardware that's required, all the computing and all the processing that's required for this sector is actually built into the display. Now everything's connected together with fibre optic, networking isn't a problem anymore, so we can actually afford to have the processing out in the display. Other than that, it's more or less exactly the same type of display. It's still a vector graphics display because that gives you a better quality of image, and the screens are still outrageously expensive. This is the sort of thing that they'll be sitting in front of at Swanwick. There's also a brand new control centre up at Prestwick as well, which does from 55 degrees north, broadly speaking, the Scottish border. What's interesting to note is, as another example of resilience, is that the Prestwick, with a certain amount of hassle, could do all the work that's being done at Swanwick, and Swanwick could do all the work that's being done at Prestwick. It would take a bit of doing, but if for any reason one or other of the control centres was unable to function, then the whole of the air traffic control in the UK could be run from one or from the other. One of the things that I decided I'd try and do was to write a game where the computer played Monopoly. And you can see here the high-speed printers. These printers would run at 600 lines per minute. I wrote this whole thing in assembler. The computer would make a move, and it would then print the Monopoly board. So this thing was throwing up pages like mad.